welcome to this problem walkthrough. Today, we're diving into LeetCode problem number 1029, two-city scheduling. This is a fascinating optimization problem that challenges us to minimize the cost of sending people to two cities while considering constraints. Let's break it down step by step and explore the best approaches to solve it. Ready? Let's get started. This problem involves a company that needs to fly exactly 2 people to two different cities, A and B. For each person, the cost of flying them to city A is given as costs, I, 0, and the cost of flying them to city B is given as costs, I, 1. The challenge is to assign exactly N people to city A and N people to city B while minimizing the total cost of all flights. To solve this, you'll need to write a function that calculates the minimum possible total cost. The input is a list of lists, where each inner list contains 2 integers representing the costs for city A and city B for a specific person. The length of this list is 2n, where n is between 1 and 100. The output should be a single integer representing the minimum total cost of dividing the group evenly between the two cities. Let's look at an example to understand the problem better. Suppose the input costs are given as 10, 20, 30, 200, 50, 40, 70, 90. Here, we have 4 people, and 2 of them need to be sent to city A while the other 2 go to city B. To minimize the total cost, we can send the first person to city A for 10, the third person to city A for 50, the second person to city B for 200, and the fourth person to city B for 90. Adding these up gives a total cost of 110, which is the minimum possible cost for this configuration. This example demonstrates how the assignment of people to cities directly impacts the overall cost. Now, consider another example with costs equals 259, 770, 448, 54, 926, 667, 184, 139. In this case, we can minimize the cost by sending the second person to city A for 448 and the fourth person to city A for 184. Meanwhile, the first person is sent to city B for 770, and the third person is sent to city B for 667. Adding these costs together results in a total of 1859, which is the smallest possible total cost for this group. This example reinforces the importance of carefully considering the cost differences between sending each person to city A versus city B. Here's one more example to illustrate the concept. If the input costs are 515, 563, 451, 713, 537, 709, 343, 819, the optimal solution is to send the first person to city A for 515, the second person to city A for 451, the third person to city B for 709, and the fourth person to city B for 819. The total cost in this case is 515 plus 451 plus 709 plus 819, which equals 3086. This demonstrates how the minimum cost can be achieved by balancing the assignments while considering the individual costs for each person. When solving this problem, there are several constraints and edge cases to keep in mind. First, the total number of people will always be even, with exactly half going to each city. If the input size is minimal, such as when n equals 1, the algorithm must handle the smallest group correctly. Additionally, if the costs for city A and city B are equal for all individuals, the solution must split the group evenly without any bias. Finally, if there are large differences in costs between the two cities for certain individuals, the algorithm must carefully weigh these differences to ensure the total cost is minimized while still meeting the requirement of sending in people to each city. To solve the two-city scheduling problem, we'll first consider the brute force approach. Here, the idea is to generate all possible ways of sending in people to city A and the remaining n to city B. For each combination, we calculate the total cost and pick the minimum. This method guarantees that we explore all potential solutions, providing an accurate result. However, the major drawback is its computational inefficiency. The number of combinations grows exponentially, making it infeasible for larger inputs. For instance, when 2n greater than 20, the solution becomes practically unusable due to the sheer number of calculations required. Because of this, the brute force approach, while thorough, is not a viable solution for this problem. Now, let's consider the greedy approach, which takes a more efficient path. Here, we calculate the cost difference for each person between the two cities and sort the individuals based on these differences. This allows us to send the n people with the smallest differences to city A and the remaining n to city B. By focusing on minimizing the extra cost for each assignment, this approach is both efficient and intuitive. The greedy approach we just discussed has a time complexity of n log n, mainly due to the sorting step. It uses constant space if the sorting is performed in place, making it highly efficient. However, this method relies on the assumption that sorting by cost difference guarantees the optimal solution. While this assumption holds true for the two-city scheduling problem, it may not necessarily apply to other variations. For an alternative, we could consider a dynamic programming approach. In this method, we define dp I, j as the minimum cost to assign I people to city A and j to city B, using the first I plus j individuals. The state transitions depend on whether the current person goes to city A or city B. If they go to city A, the cost is derived from dp I1 j, and if they go to city B, it's based on dp I j1. The base case starts with no costs when no people are assigned. While dynamic programming ensures accurate results, it comes with significant space requirements due to the size of the dp table, and its time complexity of n squared makes it less practical for large inputs. Therefore, although dp is a structured approach, it is not the most efficient for this specific problem. Given the available methods, the greedy approach emerges as the most suitable strategy for solving the two-city scheduling problem. By sorting individuals based on the cost difference between the two cities, we ensure that the total cost is minimized. This approach works particularly well because the problem guarantees an even split of people between the cities, making the greedy solution both effective and aligned with the problem's constraints. A key insight here is recognizing the significance of the cost difference. Sorting by this metric allows us to prioritize assignments that minimize additional expenses, which is the crux of the problem. This realization that sorting alone can lead directly to the optimal solution represents the pivotal aha moment in our strategy. When comparing the approaches, the greedy method stands out for its efficiency, with a time complexity of n log n, and its simplicity, requiring minimal space. While dynamic programming offers a more exhaustive exploration of possibilities, it introduces unnecessary complexity and space overhead for this problem. Thus, the greedy strategy strikes the right balance between performance and ease of implementation. In conclusion, the greedy approach is the ideal solution for the two-city scheduling problem. It effectively balances efficiency, simplicity, and correctness, making it well-suited for problems that involve cost trade-offs and fixed constraints, such as evenly splitting people between two cities. By leveraging the cost difference as the sorting criterion, this method ensures that the total cost is minimized without unnecessary computational overhead. Its clear logic and intuitive implementation further reinforce its advantages, making it the best choice for this scenario. The problem at hand is called two-city scheduling. Here, the goal is to minimize the total cost of sending exactly n people to city A and n people to city B. We are provided with two n people, where each person has two associated costs, the cost to travel to city A and the cost to travel to city B. The challenge is to decide which n people should go to city A and which n go to city B, such that the overall cost is minimized. To tackle this, the first step is understanding the constraints. We need to ensure exactly half of the people go to each city, and this balance must be maintained regardless of the cost differences. The key insight here is that the decision boils down to evaluating the difference between the cost of sending each person to city A versus city B. Instead of trying every possible combination of assignments, which would be computationally expensive, we can focus on this difference to make an efficient decision. If the cost difference indicates a significant advantage for one city, we prioritize sending the person there. The next step involves sorting the people based on these cost differences to streamline the assignment process. Once we calculate the cost differences for each person, the next step is to sort the list of people by these differences. Sorting ensures that we prioritize individuals who benefit most from going to city A first, followed by those who are better suited for city B. After sorting, we can assign the first n people in the sorted list to city A and the remaining n people to city B. This approach guarantees that we maintain the balance of sending exactly n people to each city while minimizing the total cost. The total cost is calculated by summing the city A travel costs for the first n people, and the city B travel costs for the remaining n. Sorting by cost differences is a critical step here because it ensures that we maximize the cost savings from assigning people to their optimal city. Additionally, this method is efficient as sorting takes n log n time, which is manageable given the problem's constraints. To implement this, we can use a list of tuples to store the costs and the calculated differences for each person, making it easy to sort and index the data during the assignment process. To keep track of the costs, we can use two variables, city_A_cost and city_B_cost, which will accumulate the total costs for city A and city B, respectively. Here's how the algorithm can be implemented step by step in pseudocode. First, we calculate the cost differences for each person and sort the list based on these differences. After sorting, we assign the first n people in the sorted list to city A and the next n people to city B. While doing this, we incrementally add the corresponding costs to city_A_cost and city_B_cost. Finally, we return the total cost, which is the sum of these two variables. This pseudocode demonstrates the simplicity and efficiency of the approach. By sorting the list and iterating through it, we ensure the assignment process is both balanced and optimal, achieving the minimum possible total cost within the given constraints. Now, let's analyze the complexity of the algorithm. The most computationally expensive operation is sorting the list, which takes n log n time. Assigning people to cities by iterating through the sorted list takes n time. Therefore, the overall time complexity of the algorithm is n log n. Space complexity is n, as we store the sorted list, but in-place sorting can reduce this further. Next, let's consider some edge cases. If the costs for city A and city B are equal for all people, the sorting step has no impact, and any valid split of n people to each city will yield the same result. For cases with extreme differences, such as one city being significantly cheaper for everyone, the algorithm still ensures that only n people are sent to each city, maintaining the required balance. For very small inputs, such as n equals 1, the algorithm works seamlessly since sorting and assigning one person to each city is straightforward. These properties make the algorithm robust and effective under various scenarios. Let's look at an example to clarify the algorithm further. Suppose the input is 10, 20, 30, 200, 50, 40, 70, 80. First, we calculate the cost differences, 10 20 equals -10, 30 200 equals -170, 50 40 equals 10, and 70 80 equals -10. Next, we sort the list based on these differences, resulting in 30, 200, 10, 20, 70, 80, 50, 40. The first n equals 2 people are assigned to city A, so we take 30, 10 for city A. The next n equals 2 people are assigned to city B, so we take 80, 40 for city B. The total cost is calculated as 30 plus 10 plus 80 plus 40 equals 160. Thus, the output is 160. This example shows how sorting and dividing the list effectively balances the assignment while minimizing the total cost. The toCitySchedCost function solves the two-city scheduling problem by minimizing the total cost of sending 2 n people to 2 cities, n to city A and n to city B. The key idea is to prioritize sending people to the city where the cost difference is smallest. First, the costs array is sorted based on the cost difference between city A and city B for each person, x0, x1. Sorting ensures that the most cost-effective assignments to city A occur first, followed by city B. Next, we calculate the total cost. Since exactly n people must go to each city, the first n people in the sorted list are sent to city A, and their costs I0, are added to the total. The remaining n people are sent to city B, and their respective costs I1, are also added. Finally, the function returns total_cost, which represents the minimum cost to send n people to each city while satisfying the problem constraints. This approach has a time complexity of n log n, due to sorting, and is efficient for the given problem. This is the Java implementation for LeetCode problem number 1029, two-city scheduling. The logic mirrors the Python solution, where the costs array is sorted based on the difference between sending a person to city A versus city B. The first half of the sorted array is assigned to city A, and the second half to city B. Key differences in Java include using type declarations, the arrays.sort method with a custom comparator, and Java's array handling. The implementation is concise and follows Java conventions for readability and efficiency. Here, we start with a basic example where the input array represents the costs of sending 4 people to 2 different cities. The first step is to calculate the difference between the cost of sending each person to city A and city B. For example, the difference for the first person is 10 minus 20, which equals minus 10. Similarly, we calculate the differences for the other individuals, resulting in the array -10, minus 170, minus 10, minus 20. Once we have these differences, we sort the costs array based on them in ascending order. After sorting, the array becomes 30, 200, 70, 90, 10, 20, 50, 60. Next, we send the first half of the sorted array to city A, which corresponds to the 2 people with the smallest differences. The total cost is updated by adding 30 for the first person and 70 for the second, resulting in a running total of 100. Now, we focus on sending the remaining people to city B. These are the 2 individuals in the second half of the sorted array. Adding their costs to city B, we first include 20 for the person represented by 10, 20, followed by 60 for the person represented by 50, 60. This brings the total cost to 180. Therefore, the final output for this example is 180. Shifting to a new example, we now consider a balanced case where the costs are distributed differently. The input array is 259, 770, 448, 54, 926, 667, 184, 139. As before, we calculate the differences between the costs for each person to go to city A and city B. This yields -511, 394, 259, 45. Sorting the costs array using these differences gives us 259, 770, 184, 139, 926, 667, 448, 54. Once the costs are sorted, we assign the first half of the individuals to city A. This means the first 2 people in the sorted array, 259, 770, and 184, 139, are sent to city A. We add their respective costs, 259 and 184, to the total cost, bringing it to 443. Next, we send the remaining 2 individuals to city B. These are 926, 667, and 448, 54. Adding 667 for the first and 54 for the second to the total cost updates it to 1164. Thus, the total minimum cost for this example is 1164. Finally, we move on to an edge case where the input costs are 100, 200, 200, 100, 150, 300, 300, 150. For this edge case, we begin by calculating the cost differences between sending each individual to city A and city B. The differences are -100, 100, -150, and 150. Sorting the costs array by these differences results in 150, 300, 100, 200, 200, 100, 300, 150. Now, we assign the first half of the sorted array to city A. This means the first 2 individuals, 150, 300, and 100, 200, are sent to city A. Adding their costs, 150 and 100, gives a total cost of 250 at this stage. Then, we send the remaining 2 individuals to city B. These are 200, 100, and 300, 150. Adding 100 and 150 to the total cost updates it to 500. The final total cost for this edge case is 500. By following the same approach of calculating cost differences, sorting the array, and splitting the individuals evenly between the 2 cities based on the sorted order, we ensure the minimum possible total cost is achieved for any given input. This concludes the walkthrough of the solution for the 2-city scheduling problem. To analyze the time complexity of this solution, we start with the sorting step. The costs array is sorted using the sort method with a custom key function that calculates the difference between the costs of city A and city B for each person. Sorting an array of size 2n takes log n time as the dominant factor in the sort operation is the comparison process. The custom key function, which evaluates the difference for each element, is executed in O1 time per element, contributing a total of O n time. However, this is negligible compared to the sorting step, so it doesn't affect the overall complexity. After sorting, the next step is to sum up the costs. Assigning the first n people to city A involves a loop that iterates n times, resulting in n time. Similarly, assigning the remaining n people to city B requires another loop that also takes n time. These summation steps are linear and don't dominate the overall complexity. Therefore, the total time complexity of the solution is determined by the sorting step, which is n asterisk log n. Now, let's consider the space complexity of the solution. First, the input costs array of size 2n is given, which occupies n space. During the sorting step, Python's sort method uses timsort, which requires additional space for temporary storage. Specifically, this uses k space, where k is the size of the input array, and here k equals 2n. As a result, the sorting step also contributes n space. Beyond this, additional variables like total underscore cost and n are used, but they only require 1 constant space. Since the primary contributors to space usage are the input array and the sorting step, the total space complexity of the solution is n. To appreciate the efficiency of the current solution, let's compare it with a brute force approach. In a brute force method, we would generate all possible ways to split 2n people into two groups of n each. The number of such splits is given by the binomial coefficient c, 2n, n, which grows exponentially as n increases. For each split, we would calculate the total cost, which requires n time. This makes the total time complexity c, 2n, n, asterisk n, which becomes infeasible even for moderately large values of n. Additionally, the space complexity of such an approach would be very high due to the need to store all potential splits. On the other hand, our optimized solution avoids this inefficiency by sorting the costs array based on the difference between the costs for city A and city B. This ensures that the most cost-effective assignments are made directly. With a time complexity of n asterisk log n and a space complexity of n, the optimized approach is significantly more practical and scalable. Finally, let's examine the best, average, and worst-case scenarios for this solution. The time complexity remains consistent in all cases because it is dominated by the sorting step, which always takes n asterisk log n, regardless of the initial state of the input array. Whether the costs array is already sorted, reverse sorted, or randomly ordered, the sorting process will still require n asterisk log n time. The subsequent steps of summing costs for city A and city B involve simple loops that always take n time. These steps are not influenced by the input distribution and do not change the overall time complexity. Similarly, the space complexity is determined by the input array and the temporary storage used during sorting, both of which scale linearly with the size of the input. As a result, the space complexity remains n in all cases. This consistency across different scenarios demonstrates the robustness and efficiency of the solution. One of the most common mistakes in this problem is overlooking the given constraints. For instance, the problem guarantees that n is even and that all cost values are non-negative. These constraints simplify the problem significantly, and ignoring them can lead to unnecessary complexity or even incorrect solutions. Another mistake arises in brute force methods. When generating combinations, it's essential to ensure that exactly n people are assigned to each city. Forgetting this can result in invalid distributions. In the greedy approach, sorting the cost differences is a key step, but sorting in the wrong order, ascending when descending, is required, or vice versa, can lead to incorrect totals. Additionally, dynamic programming solutions are often overcomplicated by introducing redundant states or transitions, which can unnecessarily increase time complexity. Finally, overlooking edge cases, such as when all costs are equal or when the cost difference between two cities is extreme, can expose flaws in your logic. Testing these scenarios thoroughly is crucial to building a robust solution. When discussing this problem in an interview, it's important to highlight the trade-offs between different approaches. While brute force guarantees a correct solution, it becomes infeasible for larger values of n due to its exponential time complexity of 2 to the power of n. Demonstrating an understanding of this limitation shows your awareness of algorithm efficiency. The greedy approach is often the preferred solution because it's both intuitive and efficient. Sorting the cost differences between the two cities is a critical insight that minimizes the total cost, but it's important to clearly explain the reasoning behind the sorting logic. For example, why selecting the first n or last n elements after sorting achieves the desired result. Lastly, interviewers typically expect candidates to manually test their solutions. This includes walking through at least one example and carefully addressing edge cases, such as ties in costs or extreme values. This demonstrates both a deep understanding of the problem and attention to detail. Understanding related problems can provide valuable context and enhance your ability to solve variations of this challenge. The primary problem under discussion is LeetCode 1029, 2-city scheduling, which requires optimizing costs while adhering to constraints. Another relevant problem is LeetCode 1383, maximum performance of a team, which also leverages sorting and greedy techniques to achieve optimal results. Similarly, LeetCode 1090, largest values from labels, involves a greedy approach to maximize a sum while satisfying additional constraints. For a more complex example, LeetCode 857, minimum cost to hire K-workers, explores optimization with cost trade-offs, combining techniques like sorting and heap-based approaches. Familiarizing yourself with these problems can deepen your understanding of optimization strategies and prepare you for tackling similar challenges in interviews. There are several approaches to solving the 2-city scheduling problem, each with its own trade-offs. The brute force method involves generating all possible combinations of assignments and calculating the total costs for each. While conceptually simple, this approach has exponential time complexity, 2 to the power of n, making it impractical for larger inputs. The greedy approach is far more efficient. By calculating the cost difference for each person between the two cities, sorting these differences, and then assigning the first n people to the cheaper city A and the rest to city B, you achieve optimal results with a time complexity of n log n. Dynamic programming is another option, where you explore all valid distributions of people across the two cities. Although this approach is robust and can handle additional constraints, it is less efficient than the greedy method, with a complexity of n squared. For more complex variations, such as scenarios with more than two cities, techniques like binary search combined with prefix sums can scale effectively. However, this adds implementation complexity and is typically reserved for advanced scenarios. Great job! In this walkthrough, we tackled the 2-city scheduling problem by breaking it into manageable steps and using a greedy algorithm for optimization. Remember, sorting is often a key to solving these kinds of problems. Keep practicing, and don't forget to apply these concepts to similar challenges. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!